let us see the work energy theorem for a particle. So let us consider a particle which is constrained to move along this wire frame. So initially we have a particle or we have a collar which I can constrain to move from position A1 to A2. So this collar can be moved from the position A1 to A2. In terms of radius vector, I can say R1 to R2. This position is A1 and A2. So in the intermediate position here, the collar is here. This has a mass M and this is acted upon by a force F. Now you see this force F displaces it along ds. This is the ds vector, displacement vector, and so you see this angle is theta. So this tangential component of the force is doing the work, and we want to know that how much work it has to do in order to move from here to here. So consider a collar which is constrained to move along a wire frame from A1 position to A2 position as shown in the figure, The collar has a mass M. Now it is acted upon by an external force F, which makes an angle theta at the position zone. So the equation of motion from the Newton's law applied on this. So we get, applying Newton's law, that F tangential is mass times the acceleration in the tangential direction. We can write this Ft as mass times this dv as dv, and then ds and into ds by dt. So you can again see this tangential component of force into ds, and this ds by dt is v. So this can be further simplified. So if I write F tangential into ds is equal to mv into dv. So this can be further written as F cos theta into ds is equal to mv dv. If I multiply this and put the limits, you see this limits, S1 means the first position, this is A1, and this is position A2. This velocity here, suppose at this stage the velocity is v1, and at this position we have velocity v2. So by applying the force, I have moved from the position of v1 velocity to v2 velocity. I will write this as v1 and v2. This quantity on integration, simply a1 to a2, I can write F cos theta as F dot dr vector, and this as mv2 square by 2 minus mv1 square by 2. So this is what we got by applying Newton's law. Let us see one by one what are these terms. Now let us rewrite this equation here in a general form. In a general form, I can write F dot dr from a position R1 to R2 when I say R1 is the position of A1 and R2 is the position of this, that is equal to half m V2 square minus half m V1 square. So you see this term is change in the kinetic energy of the particle, and this term is the work done by the total force acting on the particle. So this theorem, this expression is called work energy theorem, and according to which the work done is equal to the change in the kinetic energy of the body. So this is the work done and this is the change in kinetic energy of the body. Now this equation can be vectorially written in as, so in complete vectorial notation, this theorem is written as f dot dr from r1 position to r2 position vector is equal to kinetic energy half m v2 dot v2 modulus. So v2 dot v2 is itself a scalar quantity, half m v1 dot v1. So v1, so no need of modulus, we can write this as, because this we can write like this also. So this is the work energy theorem for a particle. Now here there are some important points which must be mentioned regarding our derivation of this equation. Number one point, since I have derived work energy theorem for a particle, so for a particle there cannot be any internal forces. So here this work done is the only external force, we can't have internal force. So let us write some points about this. So now in the work energy theorem, that is work done from A to B, if I say, I write this as F dot dr from A to B is equal to kinetic energy, we have moved KB minus Ka. So in terms of AB we write like this. So now here this F, since I have derived this for a particle which can't have the internal forces, so when we apply work energy theorem for a system of particle, then F must include external force as well as internal force, So this must include. So when we will be talking about system of particles, then again I will derive and I will tell that that's F is. So F will be replaced by F external plus F internal. Both forces can work. So this is F total. Since I am presently talking about a particle for which this cannot be defined, so our external is the F force. Next important point. So generally some students get confused that whether work energy theorem can be applied in inertial frame or non-inertial frame. So the question is, work energy theorem can be applied in all frames, that is in all frames, that is inertial and non-inertial. So we can apply work energy theorem in all frames. So while we apply work energy theorem in non-inertial frame, then we must take the work done by the pseudo forces. So work done by pseudo forces has also to be taken into account along with the real forces. So there is no point at whether it can be applied in inertial in all frames where and all forces will do work. So all forces has to be included which can do work in our work energy theorem. Next important point senior students will raise, whether this force include conservative or non-conservative forces. So our next topic will be going to be conservative and non-conservative. Then I will answer this question. So presently I will say that it can be applied to all, whether the force is conservative, non-conservative, real, pseudo, whether the inertial frame is inertial or non-inertial, whether the force is internal or external. Any force which is capable of doing work has to be included because this is the total work done. So now we are interested in force fields, that is conservative and non-conservative force fields. So before that field, let us see what's a force field, what's a vector field, what is a scalar field. So now what's a vector field and what's a scalar field? So the region or space at which to each and every point, we can associate a vector quantity is called a vector field. So a region where we can associate a vector quantity to every point is called a vector field. What's a scalar field? If we associate a scalar quantity to each and every point, then it is a scalar field. So let us take an example. So let us first take vector field. If the vector is a force, then it will be called a force field. So you see here, this is earth. If I place a body here, it will be attracted towards the earth, and so there will be a force vector. Here I can say that there is a gravitational field. If I place a here, there is a gravitational field. If I place here, a gravitational field. So you see here, the field is very near to it, and as you go away the field is less. So very near to it the force field is more, and so such type of field, as you go away, this field will be called a gravitational field of Earth, that is a vector field F. If I take a square plate such that here I will put some steam at 100 degrees centigrade and here some ice cubes which is at 0 degree centigrade. So you see, this region will have a temperature of 50 degrees centigrade. This region will have 80 degrees centigrade. This region will have 30. This is 20. This is 90, like that. So you see, in this hot plate, we can assign to each and every point a scalar quantity called temperature. So this is a scalar field of temperature. So this is a scalar field of temperature. This is a vector field of force. So this is the vector field of force. Now, so you can see what I mean by a field. So it is the region or space to which I can associate a unit vector, and so we will call such a field. So this is a general field idea. Now we will see that what are the different types of force fields we have. So we have two types of force field. One is conservative force field and another is non-conservative force field. So now let us see conservative force field.